So when it comes to solving an exponential equation, so you might be asking yourself, why are we going back to exponential equations? Well, again, remember there's that connection that exponentials are tied together, right? They're the inverses of a log. And so we can solve exponentials using logarithms. And so there are two kind of main ways we can do that. The first one is graphically, which again uses a graph. And the second one is algebraically, which is using algebra. That's when we, subtract numbers from both sides, or we divide both sides by 2 or whatever. And so we can use either a graph or algebra to help us solve those types of equations. And we've actually done both of those methods so far in this chapter and in previous chapters. So in chapter 8, we actually kind of solved graphically quite a bit. And earlier and kind of throughout chapter 9, we've done a little bit of solving algebraically. So we'll start with graphically. So how do we do this? So I've kind of written out a couple of steps here, pretty easy for you guys to follow. The first step is that for our equation, we're going to graph each side separately. Then you're going to look where the two graphs intersect, right? Remember, intersect is just another word for touch. And then where they touch, we're going to look at specifically the x coordinate, and that coordinate is our solution. Okay, so here's how this works. This one's kind of nice. It's actually pretty simple. So example 1 says solve the equations graphically. If necessary, round to the nearest thousandth. So first of all, we need to know our decimal places. This is 3 decimal places. Again, the way I like to remember this is thousandth is 1,000, and there are 3 zeros, so that's 3 decimal places. So how we do this? Letter G, 275 times e to the power of 0.06x equals 1,000. This equation right here. So here's what we're going to do. This is all you have to do. So we're going to separate, here's my equal sign. So the left side, I'm going to graph y equals 275 times e to the 0.06 x power. I'm then going to also graph the other side, y equals 1,000. And then I'm just going to see where they intersect. So we're going to go ahead and pull up Desmos here. I'm going to zoom in on my equation. So we're going to start with the first one. So y equals 275 times e to the power of 0.06 x. And there's my exponential. And then my next one, y equals 1,000, is just going to be a horizontal line. Y equals 1,000. So now I have to go find that graph. And that one is all the way up there. So we can now just go see where they intersect, zoom in a little bit, tap on one of the graphs. Doesn't matter if you tap on the red one or the blue one, but you'll notice there's that kind of gray dot that shows up. So if I tap on that gray dot, it shows me 21.516, comma 1,000. So again, I don't really care about the y coordinate. It's the x coordinate we want. And so x equals 21.516. And that is our answer. That is the answer for that equation. If I plug in 21.516 for x, we should get 1,000. And we can pretty easily check that. So we're just going to, you don't always have to do this, but you can do this. This is a good way to kind of check to see, on a test or something, hey, did I do this right? Is plug it back in. So if we do 275 e to the 0.06 times that x, so 21.516, does it equal 1,000? Well, the nice thing is, oh my gosh, that looks like a lot. Well, just put in your calculator. Okay, you got Desmos pulled up. So we're going to do 275 e to the power of 0.06 times, got to put parentheses up here. So 0.06 times 21.516, and we can get 999.976. And is that basically 1,000? Yeah, I would say that that's pretty darn close. Again, that's just a rounding issue there. And so I think 999.976 is close enough to 1,000 that we're good and can be pretty confident that that answer is correct. Okay, so that's it. We just split the equation in half, right? We find our equal sign, split it in half, graph one side, graph the other side, see where they touch. Okay, see where they intersect. It's really that simple. So for letter E, I would recommend you try this on your own. Go ahead and pause the video and see what you get, and then you can let it play and see if you got it right. So for letter E, our first equation, right? So here's our equal sign. Our first equation, y equals 10 to the power of 2x. Our second equation, y equals 10 to the power of 4. So I'm just going to use the ones I already have here. We've got y equals 10 to the power of x. Oops, 2x. And the second one is y equals 10 to the power of 4. And so if we go back home, I'm going to hit the home button here and kind of see where we're at. Way up there, okay. Zoom back in till I can see where they intersect, tap on a line, and then we get 2, comma 10,000. Well, that was nice. Our x equals 2. And that's probably not too surprising, because if we look at this, right, we're trying to make this 10 match this 10. Well, 2x has to match 4, and yeah, 2 times 2 would give me 4. So that's not terribly surprising, but we could do it on the graph. And again, right, one of the ways we can check it is just simply plug it in. 10 times 2 to the power of 2, 10 to the power of 2 times 2. Does it equal 10 to the power of 4? Well, this is 10 to the power of 4 and 10 to the power of 4, which if we put into our calculator, we can already see it in line 2 there. 10 to the power of 4 gives us is 10,000. And are those actually equal? Yeah, they're the same thing. Okay, so we're good. And again, you don't always have to do that. This is just one way that you can check your work to see if you did that right. And so that's graphing it. Okay, that's solving by graphing. It's really nice, especially when you have access to calculators like this, to be able to just plug in the equations and then kind of just go searching for them and figure out where they intersect. Now, the next one, I'm going to get rid of Desmos here. Now, the next type, right, so that was graphically. Now trying to solve it algebraically, right? Remember, when we're solving equations algebraically, basically what we're doing is we're having to undo everything, meaning that we need to go in reverse order of operations. Okay, so remember, order of operations, right, is PEMDAS. And so when we go in reverse order, it's like, okay, is there anything that I can add or subtract first? Then is there anything I can multiply or divide? Then is there any roots or exponents? And then what can I do in the parentheses? Okay, so we kind of have to unwrap that by going in the reverse order. So the steps listed here, okay, step 1, again, our main goal is to isolate the variable, right? We're trying to get the variable by itself. So what we're going to do is we're going to look on the side of the variable, and we're going to add or subtract over anything if needed, right? We don't always have to do that, but that's the first thing we're going to look for, because that's the first thing in the reverse PEMDAS. The next thing we're going to look for is, can we multiply or divide anything over? And in exponentials, that's usually about all you really need to do. Okay, is add or subtract, and then multiply or divide. There's really not any other crazy stuff you're going to have to worry about doing first. But those are definitely the two big first steps, is add or subtract anything over, then multiply or divide. And now from there, right, now that we should have the exponential part, right, my base to the power of x, whatever, to get rid of that, right, the inverse of an exponential is the log. Okay, so the inverse of a log is exponential. The inverse of exponential is log. So we're going to take the log of both sides. And again, the log base has to be the same as the exponential. So for example, if my exponential is base 2, then I'm going to want to take log base 2. right? Or if my base is 10, I'm going to use log base 10. Okay, so my log base and my big base have to match. And then now, once that is done, that will cancel out the base, leaving us just the exponent, and now we just solve like normal. Again, is there anything we can add or subtract? Is there anything we can multiply or divide to get the x by itself? So I know that may seem kind of confusing talking through it or reading through it. I think once we go through a couple examples, you'll kind of realize, oh, that's not that bad. So example 2, solve the equations algebraically. Write the exact answer. So I do want an exact answer first. So I want to try not to round throughout. Okay, I'm going to just leave them exact. And then give an approximation to the thousandths place. So again, it tells me the thousandths place, which is 3 decimals. Just important to notice. So letter F here. 2 to the power of 2 times e to the power of x minus 1 plus 5 equals 80. So first thing we want to do, we notice that the variable is in the exponent with the base of e. Okay, and it's important to know that it's with e only, not with 2e. The 2 is separated. If the 2 and the e were together, they would have to be in parentheses. Okay, so that is important to note. That not having parentheses means it's only with the thing next to it, okay, which is the e. So we've got to get rid of everything else outside of it first. So that's going to be the last thing to go. So what we're going to do first is we're going to get rid of this plus 5. Well, how do we get rid of a plus 5? The opposite of adding is subtracting. So we're going to subtract 5 from both sides. We get 2 times e to the x minus 1 equals 75. And again, the x minus 1 is still stuck with that e. So I want to get rid of this 2 in front. And since the 2 is multiplying, the opposite of multiplying is dividing. So we're going to divide both sides by 2. And we'll get e to the x minus 1 equals 75 divided by 2 is 32.5. Just going to double check since we got a calculator here. Divided by 2, 37.5. See, we all make mistakes. And that's why we check the calculator. 37.5. And so now, and actually I'm just going to leave the calculator up for a second. So now, right, we have the exponential part by itself, right? There's nothing being multiplied, nothing being added. It's just the base with the exponent. And so now what we want to do is recognize, okay, I've got this base e, and that's kind of what I need to get rid of because I want this x up here. So how do I get rid of base e? Remember, the inverse of an exponential is a log. And so I'm going to do log base e on this side. And again, what's log base e? Well, that's just the natural log. So on the right side, I'm just going to use the natural log because it's the same thing. And so on the right side, what happens, right? Our log property, if my bases are the same, my exponent becomes my answer. So we get x minus 1 equals on the right, we get natural log of 37.5. And then now our very last step to getting x by itself, there's one more thing to do. In this case, since x is being subtracted by 1, we got to get rid of the minus 1. So the opposite of subtracting is adding. So we're just going to add 1 to both sides. And we get x equals the natural log of 37.5 plus 1. And so that right there is my exact answer, natural log of 37.5 plus 1. And now we're going to find the approximate answer. So that is approximately, and again, we'll go to our calculator here, natural log, past it, natural log 37.5 plus 1. Tells me is about 4.624. So I'm just going to actually cover that all up. And there's our answer. Okay, so the natural log of 37.5 plus 1 is my exact answer. And then the 4.624 is my approximate. Okay, and that's it. That's letter F. That's how we do it algebraically. So So I'll do another example with you guys. Letter G. We have 6 to the power of 3x equals 12. The nice thing here, right, is our exponent is with the 6, and there's actually nothing on the outside, right? There's nothing adding, subtracting on the right side. There's nothing being multiplied in front. So now all we have to do is tackle that base 6. Well, how do I undo a base 6, an exponential? That would be a log of base 6 on the left side, and then also on the right side. So on the left side, again, our big log base matches our big base, so our exponent becomes our answer here. 3x equals the log base 6 of 12. And then now the last step to getting x by itself, we just divide both sides by 3. And so x equals log of base 6 of 12 over 3. And now one thing to remember, right, is that might be, oh my gosh, depending on your calculator limitations, right, we might not be able to use log base 6. So it's also good to know, right, that log base 6 over 12 is the same as log of 12 over log of 6, right? That's using our base change formula. We're going to change that to base 10, and then our 12 is going to go up top. Our base 6 is going to go on bottom. Okay, and so we may need to use that, okay, instead. So we can obviously use that if needed. We're not going to because you guys have access to this graphing calculator for now. But that is just an important thing to remember, is that sometimes we may need to use this if our calculator can't do that. So just keep that in your minds. But we can do it on the graphing calculator. So we can go ahead and say that x is approximately whatever that comes out to. So we're going to go ahead and do the log of base 6. I'm going to go to functions. Log a is log base 6 of 12. And then divide that all by 3. It says it's approximately 0.462. So again, we have one answer that is our exact, and one is our approximate. Okay, so that's it. That's solving algebraically. So there's one more example here, letter H. This would be a good time to pause it and kind of see if you guys can do this on your own, see how far you can get on your own, and then let it play and see how you guys did. So I'll go ahead and give you guys a moment to do that now. So again, 2x minus 3 is our exponent. It's attached to the 2, so we need to get rid of everything else. So that's with the 2. There's nothing to add or subtract over here, which is good, but I do see this 3 in front. So since it's multiplying, we're going to have to undo multiplying by dividing. So we get 2 to the power of 2x minus 3 equals 8. On the left side, we have a base 2. So how do we undo a base 2? That would be a log base 2. So on the right side, I also need log base 2. This gives us, on the left, log base, big base are the same. Exponent becomes my answer. 2x minus 3 equals the log base 2 of 8. Well, one thing I want to realize here is that log base 2 of 8 is actually a really nice number. So if I kind of quickly look at my calculator, right, or again, right, if we think to ourselves, 2 to what power gives us 8, what would that be? And so if you think about it for a second, I'm sure you could come up with it if you didn't already. But that exponent needs to be a 3, and we can double check that on our calculator. Log base 2 of 8 is just 3. And so that's something that's important to notice, right, as we're doing problems like this. And some of them aren't always quite as obvious, right? This is kind of one that we've seen a couple of times now. But when we see that, right, we can use that and work with it. So we can let this be 2x minus 3 equals 3, because that's what log base 2 of 8 is. And that's a lot easier to work with and a lot easier to solve. So it might always help to check and see what that is and see if that's a nice number that you can work with. If you can't, then just leave it as a log until we're all the way done. But if you see it early, right, notice it early, you can go ahead and figure out if we can do that. So now our last steps, couple steps here. To get x by itself, we're going to add 3 to both sides, which gives us 2x equals 6. And then we can divide by the 2 in front and get x equals 3. And in this case, this is our approximation and our exact answer because it's exactly 3. So it's both our exact and our approximate. There's really no need for an approximate here. Our answer is just 3. Okay, so that's solving algebraically for letters F, G, and H.